This video will cover 1.1, Inductive and Deductive Reasoning. So most of chapter 1 is about problem solving, and we're going to be using these two types of reasoning to figure out the answer to specific problems. Okay, so before we start that, let's go ahead and give a definition for inductive reasoning. It tells us here that inductive reasoning is the process of reaching a general conclusion by examining specific examples. And this is your key word right here, specific examples. Okay, so what we're going to do is we're going to start right with an example and just kind of show you how this works. So let's say you are given a pattern. So let's do this example A, and it goes like this: 2, 4, 6, 8, and then a question mark. So most of us would be able to tell that the answer is going to be 10 because we see that this is going by twos. Okay. So thus we predict that the next number is 2. This is an example of inductive reasoning. So in this one, we would say that that question mark is going to be 10. Okay, we're reaching a general conclusion by this specific example. Okay, so let's try another one just to kind of see if we get the idea here. So now let's go ahead and do one that has just a little bit more work. 1, 3, 6, 10, 15, question mark. Okay, so this one has a little bit more that you have to think about. We can see that from here to here. Let me use a different color here. From 1 to 3, we're going up by 2. From 3 to 6, we're going up by 3. So we're adding. From 6 to 10, we're going up by 4. 10 to 5, I'm sorry, 15, we're going up by 5. So you can already kind of see the pattern here that as the numbers progress, we're adding an additional number to the one before. So it would make sense that from 15 to the next number, we're going to add 6, which means that our next number would be 21 based on the process that we see here. Okay, so this is an example of inductive reasoning. Okay, I'm going to go ahead and do another one here just to let you try it. So I recommend pausing the video here and then trying it out and then, unpause it to see if you get the right answer. So let's say we have 2, 5, 10, that's a comma by the way, 2, 5, 10, 17, 26, and we're trying to figure out the next number. Okay, so go ahead and pause the video for a few seconds, see if you can figure it out, and then go ahead, unpause and check right after. So just like the problem before, I'm going to go ahead and do kind of like what I did for letter B, because this one you can tell it's not going by the same number. Okay, so from 2 to 5, we have it went up by 3. From 5 to 10, it went up by 5. From 10 to 17, it went up by 7. From 17 to 26, it went up by 9. Okay, so you need to figure out the next one. So if you look at this pattern now, we have kind of odd numbers here, 3 and then 5 and then 7, then 9. So these are actually going up by 2. So we see that we're going up by 2. It's kind of like a multi-layered pattern here. Okay, so the next one, if I were to go up by 2, would be 11. Okay, which means that we're going to add 26 plus 11, and that would give us 37. So if you got 37, good for you. You got the correct answer, and you just used inductive reasoning. Okay, so we're going to go ahead and do a few more examples of how to use inductive reasoning because it's not just as simple as this. I'm going to go ahead and scroll down a bit. Make sure you do write everything down, okay? So let's consider this problem right here. It says, consider the following procedure. Pick a number, multiply the number by 9, add 15 to the product, divide the sum by 3, and subtract 5. So we have this procedure that we're going to use. So let's just pick a number. I'm going to pick the number 3, just because I happen to think of 3. So I'm going to start with 3. This is my number, okay? This is the number I'm choosing. And it says multiply the number by 9. So I'm going to go ahead and color code all this just so we're on the same page. So we're going to multiply this 3 by 9. So times 9, 3 times 9 is 27. Okay, so now we are on the next one. Add 15 to the product. So the product is this multiplication 3 times 9. So this is the product right here. So we're going to add 15 to that product. So 27 plus 15 is going to give me, let's see, 5 plus 7 is 12. Carry the 1, 2, 3, 4, 42. Okay, so I have 42 now. And then it says divide the sum by 3. So this was the sum right here, that plus 15 gave me 42. So I'm going to divide this by 3 now. 42 divided by 3, I believe, is going to give me 14. You can double check with the calculator if you don't believe me. And the last step says to subtract 5. So and subtract 5. So minus 5, and that gives me 14 minus 5, I believe, is 9. So my final answer here is 9. Okay, so now what? So what does this tell us? So in this problem, what we're doing is we're trying to come up with a conjecture. In other words, kind of like the conclusion based off of what we just did. So let's compare this number 3 and this number 9. What do we know about 3 to 9? So take a second here and see if we can figure something out. I'll give you a few seconds. Okay, so I know that 3, so this 3 times, it's just a different color, times 3 is going to give me that 9. So this 9 is 3 times the number as the original number. So a conjecture, or I kind of mentioned it right now, is a conclusion based off of the reasoning that we just did right here. Now, whether or not it's true, that's a different story sometimes. But in this case, this conjecture would be that we can conjecture. So I'm going to put a sentence here. We can conjecture, so, okay, that the following procedure, okay, produces a number that is 3 times the original number. So 3 times the original number. Okay, so again, based on our procedure up here, we can kind of assume, okay, that, sorry about that, with my phone. We can kind of assume that, or we conjecture that this number is just 3 times the ending result. Okay. All right. So that's another example of using induction. Let's go ahead and do one more example just to kind of see what happens when the conjecture doesn't work out as a true statement. Okay. So here I have a picture of a few circles. Okay, and then you can also find this one in your book if you care to read it here and there. And we're gonna prove that not all conjectures are necessarily true. Okay, so remember that a conjecture, as mentioned before, is the conclusion formed by using the inductive reasoning, whether, and it can or not, it can be correct and it can also be incorrect depending. Okay, so let's look at this one. This one is asking us, what is the next number here? So we have these circles, okay, and what we're doing is we're just adding dots. So if you look at the first circle, there's 1 dot. The second circle, there's 2 dots. The next circle, there's 3 dots, and then 4 dots, and so forth. So On each turn, we're adding a dot to the edge of the circle, okay? So let's kind of make a chart here. I'm going to go ahead and do a little table here on the side. It's going to be the number of dots, okay? And let's see, what could we put over here? Well, I'm going to go ahead and do the number of dots as they relate to the regions that are separated by those lines. So in the first circle, you see how we have one dot, we cannot connect it to anything. Therefore, we have one big space here. That's what I mean by the region. Okay, so this is going to be the number of regions. And I should say the max number of regions because we're maximizing the space here. So with one dot, okay, so that's going to be this dot right here, we have one huge space. So we have this entire region. Let me get a different color so you can see. We have this huge region right here. So we have one region, okay, with two dots. So we have two dots. Well, now I have a space on the top and a space on the bottom. So I can say that with two dots, I have two regions, okay? With three dots, so 1, 2, 3, I can connect them with three lines, and that gives me 1, 2, 3, 4 regions. So you kind of see how this is working out? Okay, so this was with three dots. So go ahead and pause the video now and see if you can fill out the rest of the chart, and then I'll go ahead and check your answer afterward. Okay, so with four dots, we have 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be 8 max regions. With five dots, so 1, 2, 3, 4, 5. Okay, we have a few more. Go ahead and pause the. I'm gonna go ahead and just give you the answer. You're gonna have to trust me on this one. Okay. So with five dots, if you count all these spaces, we end up with 16. Okay. And finally, with six dots, well, based on the pattern that we have here, what number would you say is the next one? So let's take a look at the pattern we can kind of see based on using inductive reasoning. Okay. So from 1 to 2, well, yeah, I know it went up by 1. This one went up by 2. This one went up by 4. This one went up by 8. So it's kind of like you can do it this way. I would probably just say multiply it instead. It's the same thing. So you can also say this was multiplied times 2 because 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. Yeah, 8 times 2 is 16. Or just double it. Same concept. But using this reasoning here, you would say, well, from here I'm going to go ahead and add 16. Or if I multiply it by 2, it would still give me 32. So using mathematics calculations, we would get 32. But we have the picture, so let's go ahead and see if that's true in fact. You're going to have to kind of stay with me on this one, okay? If you have your book, I recommend going to page 4, and this picture is actually something you might be able to see off the ones that are there, okay? So let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 in there, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and 31. So this in fact is not 32, but 31, which comes to show that our conjecture of this being 32 based on the information that we had here, okay, was not necessarily true. And that's something that leads us to our next concept here, something called a counterexample, okay? So a statement is true provided that all cases are true. So if we had said the conjecture up here for this example, well, the number of dots is just going to be multiplied times 2 to get the number of max regions per circle. That conjecture would be false based on this right here. When we have 6 dots, the number of regions actually 31, not 32, okay? So that is an example of a counterexample. If you can come up with a counterexample to a statement, one counterexample is all it takes to prove it wrong. So let's do a couple of examples using counterexample and how this works. Let's say we have, let's start with letter A here. Let's say we have that for all numbers x, okay, the absolute value of x is greater than 0. So this is the statement we're going to use. So let's just do a few examples and see what it means. By the way, in case you forgot what absolute value means, it means the distance away from 0. So for example, if I did the absolute value of -2, that would just be 2 units away from 0. So here's a quick reminder of what this means. So that you have a number line, okay? The distance from -2 all the way to 0 is still 2 units. So the way you learned it in school is that this makes everything positive. This is the reason why, because distance cannot be negative. Okay. But anyway, so this is equal to 2, and 2 is in fact greater than 0. Okay. Let's pick another number. Let's try 5. So the absolute value of 5 is still 5, and 5 is, sorry, equal to. So the absolute value of 5 is equal to 5, which is greater than 0. Oh, sorry, technical issues. All right, which is greater than 0. Okay, let's try another one. The absolute value of -234. I'm just coming up with these numbers here. So this is going to be equal to 234 because it just makes it positive number. And that in fact is greater than 0. If we want to try to get, weird, let's say the absolute value of pi. Okay, well, pi is still pi, not the kind you can eat, unfortunately. And pi is still greater than 0. So far for all of these examples, this statement is true, right? So what we need to do is find one example where it doesn't work to prove that this statement is false. So I'm going to erase that check mark because I'm going to prove to you that this is false. What if I took the absolute value, let me scroll down a bit here, okay, the absolute value of 0, okay? Well, the absolute value of 0 is equal to 0 because 0 is 0, okay? And is 0 greater than 0? Can a number be bigger than itself? No, it cannot. This is equal to, not greater than. So this right here is my counterexample, and this proves that this is not true. Not true for all numbers x. It might be true for some. So it's true for all of these. In fact, it's true for every real number except 0. So that right there is the counterexample I was referring to. Okay. So let's try a few more of these. Just try to find some counterexamples. Let's say we have, let me see. Let's do one that looks a little bit weird. So let's do x divided by x equals 1. And this is again for all numbers x. In other words, I plug in any number in there, it should work, okay? So again, like the problem before, we're gonna go ahead and just pick a number. Let's say we pick x is equal to 10. So that would be 10 divided by 10 is equal to 1, which is true, okay? Let's try a negative number, negative 100. So negative 100 divided by negative 100 is equal to 1. That is true. So I'm hoping that you're seeing the pattern here that basically anything divided by itself is equal to 1. So far these are good to go. Now let's try that weird 0 again. 0 divided by 0 is equal to 1. Is that true or not? Hopefully you know that this is not true because this is actually undefined. So again, we are proving that this is not true. So this is not true. And here is my counterexample. Okay, so that's how counterexamples work. You use them to disprove something. Okay, it could be mathematical, real life, just different situations. All right, so I believe that's it for inductive reasoning for now. I'm going to go ahead and move on to deductive reasoning because that is the other half of this lesson. So here we go, deductive reasoning. Deductive reasoning is the process of reaching a conclusion by applying general assumptions, procedures, or principles. So the difference with this one is that it's more general, not specific to one exact example. Like the ones we all did here, they were based on an example that was given or a process that was given that said pick a number, pick one specific number. So I'm actually going to piggyback off of that idea and go ahead and show you how we would use deductive reasoning for that same number example. Okay, maybe well, actually this one's a little bit different, but the same concept. So this example says to use deductive reasoning to show that the following procedure produces a number that is 3 times the original number. So if you remember, this right here is kind of like the conjecture. Oh, wrong button. This is kind of like the conjecture that we were reaching in that second example, I believe. The one with the number, let me see. This one right here. Okay, so we're trying to prove conjecture, so to speak. Okay, so let's go back to that problem. So what we're going to do is instead of actually picking a number, so here's the process. Pick a number, multiply by 6, add 10, divide by 2, and subtract 5. Instead of picking an actual, 2, 4, 6, 8, whatever, we're going to let our number equal to n. So we're going to let n be our number. Okay, I don't know how to spell number. All right, so we're going to start with that number. Let me color code this. So here is n. Okay, here's the first step, number 1. We want to first multiply that number by 6. So for step number 2, we're going to multiply this n by 6. So 6 times n, okay? And then we're going to add 10 to that product. So step number 3, forgot to label that, that was number 2. So step number 3 is to add 10 to this product. So now we have 6 times n is just 6n, 6n plus 10, okay? Next we have divide the sum by 2. So we're going to divide by 2. So step number 4 is to divide all this by 2. So 6n plus 10 divided by 2. Okay, and the last step is so number 5, subtract 5. So the step number 5 is to subtract 5. So I'm going to take all this 6n plus 10 divided by 2, and we're going to subtract 5. Okay, so just really quickly, I'm going to recap this. So I started off with number 1, which is just to pick the number. So we're going to let that number be equal to n. So there's n. And we multiply that number by 6, step number 2, so times 6. We add 10 to the product, so we're going to add 10 to that 6n. Divide the sum by 2, so divide all this by 2. And finally, subtract 5. So if you look at it visually, you're just kind of not adding, but putting another uh, process to each step, okay, another operation, I should say, okay? So now from here, we are trying to see, what does it say? We want to use deductive reasoning to show that the following procedure produces a number that is 3 times the original number. So this right here, use my other one. This is what we're trying to prove, 3 times the original number, okay? So I need to do a little bit of work because this right here looks like a royal mess. So let's do a little bit of math work here. We can factor, hopefully you remember what factoring is, okay? We can factor out here on the top, we can factor out a 2. So 6 and 10 are both divisible by 2, which means that if I divide 6n by 2, okay, so if I pull out a 2 from there, I'm left with 3n plus 10 divided by 2 is 5. Okay, so all I did is I used greatest common factor. I hope you remember that. And I took out from this 6n and this 10, I divided them by 2. So whenever you divide something out, that number goes in the front, and whatever's left over goes in here on the inside. So if you want to check it, 2 times 3n is 6n, 2 times 5 is 10. And that's how you check your work, okay? So let me get rid of that because I don't really want to see that right now, okay? So anyway, so this is going to be what we have next. Now, if you notice, we have a 2 on the top, so we have this 2 up here, and we have a 2 on the bottom. So 2 divided by 2 is 1, which means I can cross that out. So I'm left with 3n plus 5, and I still have that minus 5 on the outside, okay? Since I don't have any more multiplication or anything else that's going on here, I can get rid of these parentheses, okay? And I'm left with 3n plus 5 minus 5. And we should see that positive 5 and negative 5 are equal to 0. So that means that this is just equal to 3n. And based on the example that we did before, we can see that 3 is in fact 3 times the number. So this is what we were trying to get to. Okay, so done, proved.